So I'm going to talk about various aspects of catalysis, both in homogeneous and heterogeneous environment, and highlight the challenges that they represent for quantum chemistry. So I will start with I start with a chemical problem. So we start with molecules in the first part. In the second part, I will move more towards materials, and I will talk about metal organic frameworks. So I have a colleague in my department, Connie Lu. She's an inorganic chemist, and Connie is interested in making some compounds in which there is a metal-metal unit surrounded by a ligand. And the idea is that among these two metals, one of them, the one on the top, is the one that will be active in some chemistry. The bottom one is more a sort of supporting metal that represents an electron reservoir for the top one. And different metal-metal pairings and also different ligands, they provide a wide range of chemical properties and reactivity. So she's interested in doing some tuning through metal and ligand choice. And she has been exploring mainly compounds containing first-row transition metals. A couple, here the different colors indicate the different pairs of metals that have been made in her lab, and different ligands with, for example, a different degree of localization of charge. And I've been very lucky because Connie and I arrived at Minnesota at the same time, and we started collaborating since then. And so she was very interested in working with a theorist, because there are a lot of questions that eventually theorists can try to help with. And one of them is the following. So we have this metal pair, so it's important to have a fundamental understanding of the structure, bonding, electronic, magnetic properties of these compounds. And then eventually these can be interesting species for small molecule activation. So can we study catalytic processes? So we are going to look, today I'm going to tell you an example of this collaboration which shows what is really challenging for theory. So I'm not just going to tell you a beautiful, successful story. I'm going to tell you a struggling, frustrating story, but from which we learn and eventually we improve on our models. So we are going to look at this series of compounds, metal cobalt chloride, where the bottom metal, this metal can be manganese, iron, and cobalt. And these are the three species under consideration. This is the ligand. And then we are also going to look at the di-iron ones. And so the question, so we are, first of all, as I told you, eventually the idea is to use these for small molecule activation. But first, we have to understand the electronic structure of these species that are brand newly made in Connie's group. And so the question is, now we're going to do a little theory, 5 minutes lecture, because this is a theory audience. So which electronic structure methods can we use to study these species? Ideally, we'd like to use density functional theory in the Kohn-Sham formulation. It's simple, affordable for medium to large systems. However, there are some challenges with the Kohn-Sham DFT, and one of the unmet challenges is the treatment of so-called multi-reference systems. This means treatment of systems where there are nearly degenerate electronic states, and you cannot really choose which one is the lowest, because they are all close in energy. And also in Kohn-Sham DFT, this treatment cannot be treated by enforcing spatial and spin symmetries. So I come from the wave function world. Nowadays, thanks to Berendt, I work on MOFs. It's really thanks to Berendt. I will tell you later about it. But I come from small molecules and wave function-based methods. And so for those of you who are less familiar, I will have a little bit of a review here. So the idea is to have a wave function. If you think we start from the Hartree-Fock solution, and then we consider all possible excitations of all the electrons in all orbitals, one has the so-called full CI method. However, this is prohibitively expensive. So what we work are wave function based instead on the active space concept. The idea is that here we have all our orbitals. One selects a set of orbitals, which are called the active orbitals, and usually these are the relevant ones in a chemical process of interest, and performs a full CI within this active space. So this is the so-called complete active space method. It recovers a large part of electron correlation, the one due to the fact that there are these nearly degenerate electronic configurations. And then on top of this wave function, one, for example, performs a perturbation treatment. So perturbation theory, this is the so-called CAS-PT2 methods to recover the remaining dynamic correlation effects. And with this treatment, one can be quantitative in computing, for example, energetics along a chemical reaction, or excitation energies if one is interested in electronic spectroscopy. The problem with this method is that here we still do a full CI, and so here you see if we select, for example, number of orbital equal to a number of electrons of this size, so 12 orbitals, 12 electrons, and so on, this is the number of determinants that one has in the wave function. There is an exponential scaling with the size of the active space. So we are out of business very soon. Nowadays, this is what one can afford, even with the largest possible computer. It's not a matter of memory or computer, it's a matter of the size of these matrices that explode. And so it's not that we can do so much chemistry. So in my group, we have been working over the years in trying to simplify this concept of the complete active space. For example, using the restricted active space concept. And the idea is to, instead of allowing everything here, to have some subspaces and impose some constraints in the type of excitations that one can use. So we still have maybe the same number of orbitals that we have here, but we have fewer configurations in our wave functions, and so the calculation becomes more affordable. Even more recently, Dong-Sham and Giovanni Limani, who were in my group, now they are in Germany with Ali Alavi, worked with a generalized active space concept. And the idea here is that the user defines as many subspaces as he or she wants, and just imposes some constraints. So the idea is, again, to be able to use these huge active spaces but still contain the size of your configuration expansion. So with that little theory, there will be more theory later, but for the time being we stop. Let's go back to Connie's compounds. So Rebecca Carson, who is a student in my group, she has studied these series using these kinds of methods. And so let's start from an example with a dicobalt compound. If one considers the d electrons that emerge from the two cobalt, one has an active space of 14 electrons in 12 orbitals. These are the plots of these orbitals, their characterization. And you see here the arrows indicate the electrons. In a single configurational world, we would have, for example, these orbitals all doubly occupied, these singly, this doubly, and this single. But in this multi-determinantal approach, you see we get these natural orbital occupation numbers, which are not necessarily 2 zeros and 1. So for example, you see the sigma orbital has an occupation of 1.22 and the anti-bonding sigma star of 0.78, which means that statistically the electrons are not always here, they are there as well. We are working with quantum, so we have these different situations. Now what happens if we go to the cobalt iron? One less electrons, and we see that the electrons, the parts is removed from this orbital. And if we look at the cobalt manganese, 12 in 12, we see that the electrons is removed from this one. So far so good. Everything seems to make sense. And also with these fractional occupation numbers, one can compute also a bond order between two atoms. So, you know, in molecular orbital theory, very general theory, one thinks the bonding is occupied, the anti-bonding is empty, so you have a single bond. But in this theory, where you have these fractional occupations, your bonding as an occupation equal to 2 minus x, where x is the occupation of the anti-bonding, so that these two numbers add up to 2. And one can compute an effective bond order as the sum of these bonding minus anti-bonding divided by 2, which should be compared to the formal bond order. So this is usually an integer. This is lower than this integer. It's a lower approximation to this, but it's probably along a series. It allows you to see how much things change. So if we look at our three compounds, the one we talked about, we see, so this is the experimental metal-metal bond distance. This is the total spin, so this is a singlet, a doublet, a triplet, and this effective bond order 0.22, so very weak single bond. If you, I mean, when we looked at the orbitals, they were quite localized orbitals. So now, what about the di-iron compound, the fourth one? So Kohn, first of all, they measure the metal-metal distance significantly shorter than in the other case. They did temperature dependence of magnetic susceptibility, and they had this curve to be compared with the other ones, which basically means that this is a high spin compound with a total S total equal to 3. So the question is, can we confirm this high spin ground state for iron-iron species and eventually rationalize it? And so we started, and first of all, we are not masochistic, so before starting those very complicated KS-DFT calculations, we want to get an idea what's going on with DFT, okay? So we looked at this. We just look at the different spin states of this di-iron. This is PB with a different percent of R3-Fock exchange. And experimentally, so the septet should be the ground state. So this is what we consider our zero energy. And then you see, according to the percent of R3-Fock exchange that you have, your results are all over the map. So actually, it seems that when you go to large R3-Fock percent, these states are lower in energy. It's really quite messy. What about if, what is also interesting here, where probably the result is the best because the septet is quite low, you see still there is this big energy difference between the various states. So we said, okay, hybrid functionals, not so good. What about local and semi-local functionals? So this is the picture that you saw before. This is with various functionals, and you see, paradoxically, LSDA, which is probably not the most modern functional, is the one that behaves the best, that at least gives the septet lower. We can say that this is one typical example, and this is just one example, but there are many of these, that shows that we have a very challenging situation for DFT. These functionals, they predict all different ground states, and the differences are very large, okay? And by the way, when I tell you quintet, septet, and so on, it's what I asked the calculation to do, but if you look at the S square value at the end of your calculation, you have very highly spin contaminated outcomes. And the inorganic chemists hate that because they want to know what is the spin state. They believe in spin, okay? So they don't like this. So what about if we do this CAS-PT2 or RAS-PT2? And here we see again the different spin states as a function of the active space size. So basically, in order to have the septet as the ground state, we have to push the active space to this huge size, 12 electrons in 20 orbitals. And today I was talking with one of Clément's students about similar problems in porphyrin compounds, where it becomes a kind of art. And now we think that this is a more realistic answer because A, the septet is the lowest, and also the fact that these states are all quite close in energy, because we are just flipping a spin when we look at these different spin multiplicities. So this doesn't make any sense, okay? So probably here we are approaching the right result, but for sure this system is challenging also for this method. And also, are we converged or not? We are not sure. I could have continued there, but I think this was more a proof of concept how challenging things are. So the reason why we need to push our space to these large spaces is the following. It's explained if we look at these two different sets of molecular orbitals. This one is the set which is not sufficient, while here things start getting better. And the difference is really in this pi and pi star orbital, that if you look with this small active space, there is not enough flexibility in your wave function, and these orbitals remain quite localized on the two different transition metals. When you enlarge the active space, the wave function is more flexible, and finally you form these more delocalized bonds. But you need to have this massive active space. And so it's challenging. So to try to summarize this part, we can say that if we use these methods, CAS, RAS, GAS, and one is ready to increase the size of the active space, in principle we recover non-dynamic correlation, static correlation in a systematic way. And then we can do a PT2 treatment on top of this to recover dynamic correlation and be more quantitative. But there are certainly a lot of drawbacks in these methods. So on one side, I talked about Kohn-Sham DFT, which has the beauty of being simple, fast, but it's a mess. And what is mess is that you don't have a systematic way to improve your answer, okay? Maybe you get the right answer. 99% of the time you get it right, perhaps. But if you don't, it's not that you have this systematic way. On the other hand, you have these methods which are more systematic, but they are really expensive. So one of the questions that has fascinated me is if one could combine the best of the two worlds, so multi-reference wave functions with Kohn-Sham DFT. And other people have worked on this field, but there is one major issue with trying to merging the two worlds, and this is called the issue of double counting dynamic electron correlation. Because the thing is, the idea is that you have your wave function that accounts for static correlation and the DFT for dynamic. But if we increase the active space, we include more and more dynamic correlation. So there is the double counting issue. And also there is another issue that is the so-called symmetry dilemma. It was first discovered by Lovedean in the 50s, and I will explain this to you, and so this means that I will go back to really elementary quantum mechanics. I hope this is acceptable. So let's suppose that you are looking at the hydrogen molecule and you want to describe the potential energy curve of the hydrogen molecule. At equilibrium, we all know that the ground state is a closed shell, and you can describe it very nicely with the sigma square, one electron configuration. When you dissociate H2, to describe it properly, one would have to construct these two determinant wave functions, or two configuration wave functions, which is a linear combination of the sigma g and sigma u with equal weight. In DFT, what DFT does, in Kohn-Sham DFT, one puts one electron on one hydrogen with spin up and another electron with another hydrogen with a spin down. And so the question is, if this is my multi-reference wave function, the correct one, can I construct a DFT theory based on this? And what happens with existing Kohn-Sham functionals is that this unphysical physical broken symmetry density. So this is unphysical. However, a functional that uses this density delivers the correct energy. On the other hand, if one starts from the correct density, from the multireference wave function, the functional delivers the wrong energy. And this is because of the functional form. So this was a problem, as I told you, discussed in the early days. Purdue, Savin, and collaborators basically showed a solution to avoid this so-called symmetry dilemma. And basically what they suggested is, instead of working with a functional of the total density and the spin density, use a functional of the total density and another quantity called the on-top pair density. What is the on-top pair density? Again, here this is quite elementary. If we have the total density, spin density, for a single determinant, there is a well-defined relation between these two quantities and the on-top pair density, which is basically the spinless two-body probability density. It tells us what is the probability of finding two electrons in the same position at the same time. So this relation is valid for a single determinant wave function. So with all these premises, in collaboration with my colleague Don Truller at Minnesota, in the last couple of years, we have worked in really combining these two words, and we have developed this theory called the multi-configuration pair density functional theory. And you know, Don Truller, for those of you who know him, is a functional guy, the Minnesota functionals. And when I came to Minnesota, I am a multi-reference person. We had a pleasant disagreement in a way, in the sense that I thought that his functional parametrization was hopeless, and he thought that my multi-reference methods were also hopeless because they were unaffordable. And we have been able more recently to merge the best of the two worlds. And so we avoid the double counting of dynamic correlation. And also we solve the symmetry dilemma. So have the correct density, but also get the correct density. So this double counting of dynamic correlation is avoided by the way in which we compute the total energy of the system. So basically we perform the multi-reference calculation, and from that we just borrow, we compute the kinetic energy, classical Coulomb contribution to the total energy, and then from the multi-reference density and the on-top pair density, we construct this exchange functional, and that contains all the exchange and correlation contribution. So this could be the equivalent of exchange correlation functional in Kohn-Sham DFT. And the symmetry dilemma is avoided by using a multi-reference wave function, so we get the correct spatial and spin symmetry, but then we write the functional as a functional of rho and pi. So since maybe many of you are familiar with DFT formulation, this is a comparison between Kohn-Sham DFT and multi-configuration pair density functional theory. So in Kohn-Sham DFT, your wave function is a single Slater determinant, single configuration wave function. Here, on the other hand, we have a linear combination of different configurations or determinants. And then in Kohn-Sham DFT, you have this functional of rho, which has the kinetic energy, nuclear electron, Coulomb repulsion, and then there is the exchange correlation of rho. Here, on the other hand, we have this MC-PDFT energy, which has the kinetic is the same. The wave function is different, but it's computed in the same way. The nuclear electron attraction, it's computed in the same way. Of course, it's a different density because this is a density that comes from a multi-reference wave function. Electron Coulombic repulsion, same. And then instead of having this exchange correlation of rho, we have this on-top energy of rho and pi. So in terms of these functionals, E of rho and pi, eventually we will develop functionals of these two quantities directly. But at the moment, we are still really borrowing some tools from Kohn-Sham DFT, and we just take exchange correlation functionals of spin density, so from Kohn-Sham DFT, and translate them using that prescription, that relation between rho and m on one side and pi on the other. So we basically, I will show you results with what I call TPB, translated PB. So how does this theory work? So this was our first attempt. Here you see this is a series of systems. These are chemical energies, 46 systems. And what is reported here is the mean average error in kilocalories per mole. And we have here the Kohn-Sham DFT results, some common, well-known functionals. Here we have the wave function world, the CAS-PT2. So this is the kind of accuracy that we would like to have, but it's very expensive. And also going from here to there, one has to pay a significant price. This is a MC-PDFT, which should give results of this quality, but at a much lower cost. So the bottleneck in this calculation is the KS-DFT or equivalent calculation, but the cost is significantly less than in this case. So this is quite promising. We have also, as I told you, we are interested in breaking bonds, but also, for example, electronic excitation. And this is a benchmark of these are 23 electronic excitations, and this includes typical cases which are challenging for Kohn-Sham DFT. So both Rydberg states and charge transfer states, but also valence. And this is the average mean unsigned error. And you see CAS-PT2, this is what one usually gets with this kind of methods, a multi-reference wave function followed by perturbation theory. This is what one gets with PB or PB0, and this is what we get with our translated PB. So it's similar quality to CAS-PT2, but much cheaper and significantly better than the parent functional, which is PB. So I told you at the beginning that we like to use not just the CAS, here these are CAS calculations, but also this simplified multi-reference wave function. So the question is, can this simplified multi-reference wave function work within this DFT framework? And so we have really tried to look at a very simple case of this gas SCF, which we have called the separated pair approximation. So the idea here is to create classes of orbitals, and in each class one puts a bonding, an anti-bonding, or a bonding, non-bonding, and not allow inter-subspace excitations. So you can think of this as similarities with generalized valence bond theory, but within each subspace we allow more freedom, so also triplet states, for example, if we want overall a singlet wave function, are allowed. And so this allows to break bonds correctly, while generalized valence bond theory doesn't. So to give you an example, this is a simple molecule. It's the C2 molecule. Let's suppose that you want to do a full valence calculation. You'd have an active space of 8 electrons in 8 orbitals. These are your orbitals. And this is the dominant electronic configuration. So this is your CAS 8 in 8, 1,700 configurations. If we partition the orbitals in these subspaces and we allow excitations only within each subspace, we get only 150 configuration state functions instead of 1,700. So the idea is, can we use this as a reference wave function to do MC-PDFT? How does it work? And so here Sam Odo studied the dissociation energies of various diatomics, and what is reported here, these are difference from experiments in kilocalories per mole. So the larger these bars, the worse the method is. And you see just the parent wave function KS-DFT is quite bad, but when you go you do PT2 on top of that, wonderful, okay? But what about, so CAS-TPB is this translated PB using this wave function, and it's quite good. If instead we use this separated pair approximation, you see it's pretty bad, but when you do a SP-TPB, the quality of these results are similar to CAS-TPB. So it seems one can start from these cheaper reference wave functions and get reasonable results. And still, I think it's interesting to compare these two sets of results with the traditional Kohn-Sham PB. We are also looking at this method for transition metals. These are preliminary results. And you see these are diatomics including transition metals. This is, for example, the molecular orbitals used in this copper hydride. If you partition them in these subgroups, you see again the mean average error. It's very large if you just use the parent wave function, but then when you do this MC-PDFT with the two wave functions, the results are similar to CAS-PT2. So to summarize this part of my talk, what is new in this new theory is really the way in which the total energy is computed by adding some contributions from the multi-reference wave functions and some from the functional. And in such a way, there is no double counting of correlation energy because the correlation energy comes all from the functional. It describes multi-configurational systems with no ambiguities about which state is being approximated, what the inorganic chemists, as I told you, love. And it scales as the initial calculation, but it produces results of this quality, which is quite promising. Of course, there is a lot of development that still needs to be performed. So investigate the dependence on the active space choice. Optimize the functionals. Eventually, we'll develop functionals of rho and pi directly. But first, we have to understand better the active space dependence. At the moment, this is a post-SCF theory. We just do our CAS-SCF or whatever calculation, and then we compute the on-top energy post-SCF. So we want to do it. We want to go beyond this formulation. And we are also working in developing analytical gradients. This is important to generate potential energy surfaces for excited states. So this could perhaps become an alternative to, or not an alternative, but especially in challenging cases, to time-dependent density functional theory. So while I talked about Kohn-Sham compound, I said that they could be used for catalysis. I just want to wrap up this story and tell you that once we look at these species, we looked at their catalytic properties as well. And so, for example, one reaction that we looked at is the silylation of N2 with this trimetic silicon chloride and the dicobalt species. And what we do in my group is to consider a possible catalytic mechanism and really look at this reaction step by step. So this is, for example, the energy profile for this cycle that shows that this reaction occurs downhill, and so this catalyst seems to be very promising for this type of reaction, better than some more commercial catalysts. And in general, when we perform these calculations, we explore the entire potential energy surface with density functional theory, and then when we have, for example, transition state structures or structures that can have challenges, we move to these more expensive methods. So to summarize this part about these dicobalt compounds, they can be effective for N2 functionalizations, and we are really working in collaboration with Connie to tune the active center in these bimetallic systems and look at isostructural families of these compounds, and from a theory point of view, explain their electronic structure and then propose catalytic mechanisms. I gave 2 topics in my talk, so I have to move to the second topic. I think I have another 15 minutes or so. And this is more moving from homogeneous systems more towards materials. And the idea is, I come more from the small world. I tell you, I study H2 most of the time when I want to understand how a method performs. But the idea is, can we migrate to this more complex world by trying to bring some of the knowledge that we learn from small systems? And so I'm going to talk about catalysis using metal organic framework. And I must say that, honestly, if I work in this project, it's thanks to Bernd. Because before meeting him, I didn't even know what a metal organic framework was. And now we have a center on metal organic framework in Minnesota, so I really owe you a lot. But let's first of all talk about the class of reactions. So this is a collaborative effort in the United States. It's an energy frontier research center, similar to what Bernd was directing when he was in Berkeley. And it's called Inorganometallic Catalyst Design Center. We have promised to the Department of Energy that we will come up with the next generation of catalysts, and we are focusing on a special class of reactions. They are related to natural gas conversion. So the reactions of interest, so it's different compared to what I talked before, are, for example, selective oxidation of light alkanes to alcohol, for example, methane to methanol, dehydrogenation of light alkanes to give alkenes, and hydrogenation. In general, we can talk about the manipulation of carbon-carbon bonds. The motivation for that is that in the US there is an enormous increase in shale gas extraction, as for example shown by this picture. So one would like to convert natural gas from gas to and vapor to liquid, but this is certainly a challenge. So one needs to develop new catalysts, and maybe I should go off record, but I'd like to say we are lucky that we picked this class of reactions. Honestly, we would like to develop new materials for every type of reactions, but maybe these reactions will still be appreciated in the new administration of the United States, right? Imagine if we were working on carbon capture, what would happen today, or on green energy. Okay, please delete this from the record. So, what type of catalysts are we interested in? So the idea is the following. We want to have catalysts which are well-defined and uniform in structure and composition, but also they are isolated one from the other. And ideally, they are great both for experimental structural characterization and computational modeling. So the idea is the following. One has a support, and we are specifically focusing on metal organic frameworks. And in these supports, there are these units. They are called these nodes. I will tell you more about them. And in principle, one can, these are metal oxides, small clusters, and can maybe modify them somehow, and then add a small metal or metal cluster, really of atomic precision. And this overall will be our catalyst. And the idea is that it's the ensemble of the small metal cluster and the support that act as catalysts. They influence each other. And also we have this rigid structure, so these metal clusters are well isolated from each other and eventually easy to characterize. So what about metal organic frameworks? Well, I'm sure you are familiar with them, but for those who are less familiar, these are hybrid solids, and they are formed by organic linkers. And you see them here. And then there are nodes, and the nodes are made out of inorganic metals or metal-containing clusters. And one can change the metal and the linker and, in principle, generate millions of different MOFs. And this material design is one of the topics on which Bernd also has been working and is a leader in the field. So the the experimental collaborators on this project are at the university, Northwestern University, and they are Omar Farah and Joe Happ. They are some of the MOF people. Of course, here we have also a MOF synthesis person, Kyriakos, so it's a big community, very competitive, and so on. We collaborate with Omar and Joe, and they make some of these materials. We are going to look now at some chemistry using the so-called Ni-NU-1000 MOF. NU stands for Northwestern. So in this particular material, the node, the inorganic node, is this zirconia oxide system, and these zirconia nodes are connected by these tetracarboxylate linkers. And here you can see an idea of the dimensions of these pores. So these materials have pores in various directions. In this case, we have a pore which is about 30 Armstrong and one which is about 8 Armstrong. So once they make the material, they want to activate it for various applications. For example, with the deposition of a metal onto the internal surface. And this deposition can be performed through various techniques, for example, atomic layer deposition or solution exchange. And then, as I told you, the ensemble of the deposited metal and the node acts as a catalyst for various reactions of interest to the center. So what are the challenges for theory? Because, we look at this problem from a theoretical perspective. So first of all, we have to find a model and a method adequate to describe the entire system, which is the support plus the deposited metal cluster. And then we have to look at catalysis. So we have to follow various reaction paths. I showed you very quickly what we do in homogeneous, something similar. And then maybe we have these metal clusters, which may have a very complex electronic structure because they are open shell. And ideally, this is what we have promised to achieve in 4 years. I'm not sure we will succeed in 4 years. Go from a case-by-case description to this high-throughput procedure. We press a button and we know what's the best catalyst for a given reaction. So first of all, okay, we want to look at these local effects. Can we work with a cluster model? And so we have our node. Design a cluster that represents the node. And then what experimentally, they have this zirconia oxide with the linkers, and then experimentally they know that there are 16 protons, but they don't know what is the proton topology because this is not something that you can detect with the X-ray. So they ask us, can you tell us what the proton topology is? And then go from this system either isolated or decorated and study the catalysis. And eventually, to go from the case-by-case to the general, instead of doing everything again from scratch, can we identify some descriptors to establish a structure-functions relationship? I'm sure it's the same that you do in Marvel with different class of materials and different problems. So we were able to understand the proton topology of the node, and I will not tell you this story because it's a long story by itself. I want to move to the catalysis part. So this is our node. We basically, through the interplay between theory and experiment, have established that there are both OH groups and, like here, and water groups. And so there are hydrogens with different characters. So here, for example, we can say that this is our hydrogen, which is hydrogen bonded between two oxygen. This is a water hydrogen. This is a OH hydrogen. This is a mu-OH hydrogen. And then we activate the material with a metal precursor. And so the question is, the metal can be deposited through these techniques. These 4 hydrogens can be replaced by the metal. Which one goes first? And here the calculation can reveal how the metal precursor binds the node. So all this, we have studied it extensively. To conclude, I will just show you a little bit of catalysis. And this is having this node with a cobalt versus nickel catalysts attach and study the catalytic activity for dimerization. This work has been performed by Varinia Bernales, who is a postdoc in my group, and Aaron League, who works with one of my colleagues at Minnesota. So what Aaron and Varinia has done is study the homogeneous catalysis literature and look at all possible pathways for this ethylene dimerization with cobalt or nickel. And they have explored all of them, and this seems to be the catalytic cycle, the most favorable energetically, which basically involves a pre-activation of the metal. So here Ni-NU-1000 is our support, and here we have our metal, which could be cobalt or nickel, and then there is the first ethylene molecule insertion, a beta hydrogen elimination step, another insertion, and the regeneration of the catalyst. And so they say, okay, this seems the most plausible mechanism, and here there are the energetics of these various steps. So we have enthalpy as a function of a reaction coordinate. And here we have cobalt versus nickel. So what is interesting to notice here is that the relative energetics are quite different in the two cases. Usually in catalysis, one is interested in the rate determining steps, which is the highest possible barrier, and in this case it is transition state from 2 to 3. And you see in the cobalt case it's significantly higher than in the nickel case. So experimentally, they can see more catalytic activity with nickel than with cobalt, and I will come back to the experiment a little later. So in principle we can say, okay, we agree with that, we have a lower barrier for nickel than with cobalt, so fine. But we are really interested not just in getting numbers, but also understanding where these differences come from. And so we looked at this transition state in particular, and if you look at the cobalt versus nickel structure, you see that cobalt, you have these, these are 2+ transition metals. So cobalt is a D7. The geometry is, sorry, it's here. It's trigonal bipyramidal, and the metal is in high spin state. On the other hand, if you look at the nickel 2+, it's D8. The geometry is square planar, and the metal center is low spin. So basically, you have these different electronic configurations, which is responsible for the different geometry, and then we perform this more advanced multi-reference calculation. And if we look at the molecular orbital picture, we see that in cobalt, all the d orbitals are either occupied or partially occupied, while in the nickel, this is not the case because we have the low spin. And so if we look at the interaction between the d orbitals of the metal and the ethylene, we see that the fact that we have this empty d orbital stabilizes the pi to sigma of the figure is a little large, but bonding interaction, bond formation in the transition state. And here you see this is the analysis of the wave function in the two cases. You see that in the nickel you have more d participation than in the cobalt case. So we were able to explain this difference in terms of electronic structure. However, now let's go back and have a reality check with experiment. So experimentally, they deposited these metals with AIM is atomic layer deposition in MOF. So it's this gas phase experiment. And what they measure is that the turnover frequency for cobalt is about 5 times lower than that for nickel. So it's true that cobalt is less active, but if from this data you also compute the Arrhenius activation energy, one notices that for cobalt it is about 4 kilocalories per mole higher than for nickel. So these data do not at all correspond to what we calculate, in the sense that our energy differences between cobalt and nickel is much higher than what detected experimentally. I mean, our energy difference would give a difference in turnover frequencies of several orders of magnitude larger than here. So all this makes us think that we have worked with this monometallic model, but this is probably not what they are measuring experimentally. They have probably a small metal cluster, a small nickel or cobalt cluster attached to the node rather than a single metal catalyst. And so we are moving into the direction of modeling these more complex systems experimentally. They are attempting really to achieve this single metal catalyst by other techniques. But overall, I want to tell you that this is more complex than probably what we started with. Bruce Gates, in the center, is also looking at some noble metals for the same type of reaction. So he's looking at iridium catalyst for hydrogenation and oligomerization. And again, he has this precursor with your node, and he deposits there. And what is interesting for this kind of compounds, again, we can model it, but it's a can we establish some relationship between some properties, and in this case the carbon is stretching frequencies in the precatalyst and the catalytic activity for ethylene oligomerization. And so if we can establish these relationships, can we then design a better catalyst? And a lot of work is going on in this direction. I just want to show you a final slide in which basically you see, if we look, so if this CO stretching frequency is a descriptor, is somehow related to the catalytic activity, if we have, this is what you have, iridium on just metal oxide surfaces. So you want to go to high frequency, high selectivity. This is what people use routinely, also industrially. So if we put iridium at the node of Ni-1000, we are here, which is better than the conventional metal oxide, but much worse than the zeolite. If we pre-decorate our node with aluminum, we see that we are moving in the right direction, and then we attach iridium there. That said, our goal is, so this is the iridium at Ni-1000, the node. This is the iridium in which between the zirconium and the iridium, one has put a layer of alumina, trying to mimic more the zeolite type of environment. Again, our goal is not to overcome this. That may be done by a startup or by some company, but try to understand these fundamental principles to do catalyst design. So to summarize, and then I'm done, we have been looking at these mononuclear species. We have to start simple. We have elucidated the reaction mechanism and understand the correlation between electronic structure and the turnover limiting reaction step. However, this is a very simplistic approach. We need to look at these more polynuclear clusters and also explore more catalytic reactions. Some people think that hydrogenation or dehydrogenation are toy reactions. They are not very relevant to catalysis, but I think they are. And then come up with some descriptions like charges, frequencies, to establish this loop between theory and experiment. With that, I'd like to conclude. So this is my group at Minnesota. And so today I've talked about the work of many people. Varinia, Josh, Kostas, and Sam are involved in the Metal Organic Framework project. Chad and Rebecca on the multi-configurational pair density functional theory development, and I have the pleasure to collaborate with many people at Minnesota, Connie Liu in organic chemists, Don Truller and Chris Kramer, they are theorists, and then Joe Hupp, Omar Farah at Northwestern University, and Bruce Gates at UC Davis. And I'd also like to thank you, the Department of Energy, for the funding, and all of you for your attention.